All right, today we are going to be discussing normal distributions, again, for a second time. So let's start with this review example. The heights of adult men in the United States is approximately normally distributed with a mean of 70 inches and a standard deviation of 3 inches. We will be finding some z-scores here in just a second, but first thing we should do anytime we are given a normal distribution, at least at this beginning stage where we're still getting used to it, is draw a picture of that normal distribution. Remember, normal distributions are bell-shaped, symmetric, unimodal, all that good stuff. They are centered at the mean, so in this case that mean is 70. The distance from the center to the inflection point, or about halfway down the little hill, is 1 standard deviation. In this case, the standard deviation is 3 inches, so this mark would be 73 inches. Go that distance again, 76, again, 79, etc., etc. Now, 1 standard deviation below that mean, that same distance but below the mean, again, about the inflection point, is going to be 67. Below that, 64. Below that, 61. It does technically continue, but drawing 3 standard deviations above and below the mean is generally sufficient. Now, let's find some z-scores. In case you have forgotten, the formula for a z-score is x minus mu divided by sigma, where x is the data value you are calculating the z-score for, mu is the population mean, and sigma is the population standard deviation. So the z-score for 72 inches would be 72 minus 70 divided by 3. So in this case, that would be 2/3. Now, when we use our table, we're going to have to convert that to a decimal, so we can convert that to 0.67. All right, 65 inches, we're going to follow the exact same format. 65 minus 70 divided by 3. So that is going to be negative 5/3, which is negative 1.67. To find these next two, we're first going to have to convert from feet into inches. 6 feet 4 inches is the same as 76 inches. So our z-score is going to be 76 minus 70 divided by 3, or exactly 2. 5'9" is 69 inches. So that z-score is going to be 69 minus 70 divided by 3, or negative 1/3, or negative 0.33. Right? As a reminder, what a z-score tells us, it's also known as a standardized value. It tells us how many standard deviations above or below the mean a particular data value is. So 72 inches is 0.67 standard deviations above the mean. 5'9" is negative 0.33 standard deviations below the mean. Okay? So now let's find some probabilities. All right? X is the height of a randomly selected adult man in the United States. We want to find the probability that that person has a height greater than 72 inches, less than or equal to 76 inches, or between 65 and 69 inches. All right? The way we are going to do this is by calculating a z-score and using the standard normal table like we talked about last time. So 72, we're going to take that value and convert that to a z-score, which we actually already did up above. So this is actually going to be equal to the area to the right of 0.67. The probability that x, the height of a randomly selected adult man, is greater than 72 is going to be the exact same as the probability that your z-score is above 0.67. So we can come over here to the standard normal table. Remember, this is in your formula sheet. We find the negative 0.6 row, come over to the 0.07 column, And the z-score, or excuse me, the area to the left, hold up. Sorry, we wanted positive 0.67. That didn't seem right. So, my bad. Come down here to the positive numbers. Positive 0.6, column for 0.07. Area to the left is 0.7486. Okay? So the area to the left is 0.7486, I believe it was. Let me just double check. Yep. So to find the area to the right, we just need to do 1 minus that, and we get our probability of 0.2514. All right. Next one, we want to find the probability that a randomly selected man is less than or equal to 76 inches tall. Does that equal to actually matter? No. As we talked about last time, a normal distribution is a continuous curve, so it's not possible for a value to be exactly equal to any specific number. So that equal sign doesn't actually affect anything. So we are going to find the z-score for 76, which we already did. It is 2, which means we need to find the probability that z is less than 2. The height is less than 76 is going to be equivalent to the probability that z is less than 2. So once again, we come back to our table. We find the 2.0 row, the 0.00 column, and the area to the left of that value is 0.9772. 0.9772, so roughly 97.72% of adult men in the United States are less than 76 inches tall. Now, to find the probability that x is in between 65 and 69 inches, we would need to do a couple of things. Find 2 z-scores, one for 65, one for 69. Again, we already found those. So this is the equivalent of the probability that z is between negative 1.67 and negative 0.33. All right. To find this, we find the area to the left of the larger z-score and subtract the area to the left of the smaller z-score. So the area to the left of negative 0.33 right here, 0.3707 minus the area to the left of negative 1.67 is 0.0475. And I'm going to type that one into a calculator real quick. .3232. All right, great. So here is some more review that I would welcome you trying on your own, finding these areas. Just, the probability z is between negative 2 and 2, to the right of 3.25, etc., etc. Okay. I'm going to skip going over those, but you are welcome to try that on your own. I think it would be great practice. Now is also an okay time to pause this video and go watch another video I made going over how to use a calculator to get normal probabilities. It's a little bit faster. That way you don't have to use the standard normal table every time. So now would be a great time to pause this video, go watch that one, and then come back to this one where we go through these other examples real quick. All right. So I'm going to assume that you have done that, and I'm going to start using a calculator from here on out to get these probabilities. All right, so let's look at an example that is a little bit, well, similar to the one we just did, I guess. SAT scores of high school seniors in Utah are approximately normally distributed with a mean of 1,238 and a standard deviation of 185. If a high school senior in Utah is selected at random, find the following probabilities that they scored above 1,400, and then other ones. Real quick, let's draw our picture to give us a little bit more space. I'll come over here this time. All right, the center of our distribution is 1,238. One standard deviation above that would be 1,238 plus 185. So 1,423. One standard deviation above that, 1,608. And one above that, 1,793. Now, one standard deviation below the mean would be 1,053. One below that, 868. And one below that, 683. Okay. Now, if we want to find the probability that they scored above 1,400, that is roughly this probability right here, that area. Now, we could find a z-score, go use the standard normal table, or we could just use our calculator, which on our homework in your notes, you don't need to show a ton of work necessarily, but on the AP test, if you wanted to do this, you would have to write it out like this. Normal CDF, lower equals, in this case, that would be 1,400, upper equals 1 times 10 to the 99th power, mu equals 1,238, sigma equals 185. And if you type that into your calculator, hold on. You get your probability of 0.1906. All right, finding the probability that they scored below 1,000, do that in red. That would be roughly this probability right here. Okay. Once again, if you use a calculator, you'd have to write it out that way. I don't particularly want to write it all out again, so you guys can do that on your own, I believe. I believe in you. You can do it. Hold on. Oh my gosh. Wrong button. Zero 0.0991, I guess. Probability that they scored between 100 and 1,400. Again, pretty straightforward to get in your calculator. Use 100 as the lower bound, 1,400 as the upper bound. Same mean, same standard deviation as before. That gives us a probability of 0.8094. Okay, so now let's talk about how to find percentiles. All right, this one is going to be a little bit different. The 90th percentile, that is the score that has 90% of the distribution at or below it. Okay, so now we're not looking for an area or probability. We know that probability is 0.9. We need to find the value that has that probability. So again, refer back to the video that I made about how to use your calculator for this. but use that inverse normal, 0.9, mean of 1238, standard deviation 185. And we find that the 90th percentile is 1,475.087. Now, you might not know this about SAT scores, but they don't do decimals, so really we can just round this to the nearest whole number, which in this case is 1,475. So that is the 90th percentile. The chance that they did better than that by definition would be 10%, right? 10% of people did better than 1475. Now, what is the probability they scored worse than the 25th percentile? Well, by definition, that's going to be 25%. What is the 25th percentile? Well, to do that, we're going to have to use that inverse normal function again. Sorry, 0.25, 1238, 185. So the 25th percentile is a score of 1,113. All right. Now, last example, or last couple of examples, sorry, is combining normal random variables. Now, the good news is that the rules we talked about in Unit 4, discrete random variables, still apply here with continuous random variables. If you are adding random variables together, you can just add their means, and that's going to be the mean of the new combined random variable. You cannot, however, do that with the standard deviation. Okay, if we let z equal x plus y, the mean of z is just the mean of x plus the mean of y, but the standard deviation of z is going to be the square root of the sum of the variances of x and y. Okay? Yeah. Anyway, so let's take a look at this example. Suppose a certain variety of apples have weights that follow a normal distribution with a mean of 9 and a standard deviation of 1.5. If bags of apples are filled by randomly selecting 12 apples, what is the probability that a bag weighs less than 100 ounces? So here we have a random variable. Let's say x is, weight of an apple. The mean of x is 9 ounces, and the standard deviation of x is 1.5. Okay? Let's define y as the weight of a bag of apples. So y is going to be equal to x1 plus x2 plus x3 plus all the way up to x12, because we are putting 12 apples into a bag. So the mean of y is going to be the mean of x1 plus the mean of x2 plus all the way up to the mean of x12. Each of those has a mean of 9, so that's 9 plus 9 plus 9, 12 times, which is 108. So the mean of y is 108. The standard deviation of y is going to be the square root of the variance of x1 plus the variance of x2 plus the variance of x3, etc., etc. So that's going to be the square root of 1.5 squared plus 1.5 squared 12 times. If you type that into a calculator, you get about 5.2. Okay, so y is still going to follow a normal distribution because it's the sum of normal random variables. It's going to have a mean of 108 with a standard deviation of 5.2. So your normal distribution looks something like this. We want the probability that the bag weighs less than 100 ounces. All right? So we can once again use our calculator, lower bound of -1 times 10 to the 99th power, upper bound of 100, mean of 108, standard deviation of 5.2. And we find that the probability is, I don't know if that notification sound came through for you guys or just on my headphones, but that was quite loud. Apologies. The probability is 0.062. Okay, great job. All right, last example. Runners on the high school track team will compete in the 4x400 relay. Each runner's individual time is approximately normally distributed according to the following table. Find the probability that the team finishes the race in under 223 seconds. All right, so the total time for the race is going to be equal to the time of runner 1 plus the time of runner 2 plus the time of runner 3 plus the time of runner 4. Okay. Now the average total time for this relay is going to be the average for runner 1 plus the average for runner 2 plus the average for runner 3 plus the average for runner 4. I don't know why it's so delayed. All right, the average for runner 1 is 58 seconds, runner 2 is 61, runner 3 is 57, runner 4 is 53. So that gives us an average total time of 229 seconds. Now we got to get the standard deviation for the team's total time. That's going to be the square root of the sum of the variances. Runner 1 has a variance of 2 squared. Runner 2 has a variance of 4 squared. Runner 3 has a variance of 3 squared. And runner 5 has a variance of 5 squared. Type all that into a calculator and you get 7.35. So the team's total time follows a normal distribution, because this is a sum of normal random variables with a mean of 229, a standard deviation of 7.35. So that would be like that. Okay. We want to find the probability that their time is less than 223 seconds. So again, use that calculator. Lower bound -1 times 10 to the 99th power. Upper bound of 223. Mean of 229. Standard deviation 7.35. So this chance is about a 0.207. It's about 20% of the time this high school track team will run their relay in less than 223 seconds.